Now that we know how exponential modeling works for both growth and decay, let's think about how we want to compare it to linear modeling, which we did in chapters 2 and 3. So remember that the increase or decrease of a linear function is additive. So we say the dependent variable increases or decreases by a numerical amount per unit increase in the independent variable. In other words, we'd say things like, for every year, this thing is going up by this amount every year, or going down by this amount every year. But with exponential models, the increase or decrease is multiplicative. And the easiest way to describe that is the percent increase or percent decrease per unit increase in the independent variable. That's why I said back here, right here, every hour, the amount of acetaminophen in the body is decreasing by 24%. You're losing 24% every hour. Or back here, the amount of money is increasing by 4%. And then every year is that independent variable, talking about time in this instance. Okay, so now let's see if we could do both of them together. So we have the population of the U.S. Virgin Islands in thousands at T years since 2008 can be modeled by this model right here. And we are going to explain either the meaning of m and b for a linear function or a and b for an exponential function. Okay, well, this is obviously an exponential function, so let's explain it. So we've got a equals 108, so we're going to explain that one first. What does that mean? The population of the U.S. Virgin Islands was 108,000, because it's in thousands, in 2008. Thousand. All right, so there we've got A explained. Let's look at B. B equals 0.73. Now remember what you can do here. That means that that's 73%. So B equals 73%. Take it away, or take away 100%. And that would give you negative 27%. Keep that in mind for future reference. Oh, here. Sorry, that's not a correct mathematical statement. I don't want to say that. It's not that B is negative 27%. So let me just erase that part. So B equals 73% or 0.73. There we go. So what does that mean? Every year, because time, again, is our independent variable, the population of the U.S. Virgin Islands is decreasing by 27%. And of course it didn't fit in. That would just make my life too easy. Decreasing by 27%. There we go. Oh, it did fit. No, it didn't. There it is. All right, so we've got A and B explained, an exponential model. So I bet a linear one's next. Yep, sure enough it is. Okay, so the number of single-father households in the U.S. in thousands at T years since 1960 can be modeled by this. Single-father households is a U.S. Census distinction, by the way. It means a household with minor children that are headed by a single father. In other words, there's no mother and there are children. Okay, so we have M and B to explain. So let's start with B. B is easier in this case. It is 297. 297. Okay, so that's the y-intercept for a linear function. So in 1960, there were 297,000, because again it's in thousands, single father households in the U.S. Households in the U.S. All right, now M equals 46.51. Okay, so every year the number of single father households in the U.S. increases by 46.51 thousand. Right? Every year there are 46,000 more single father households. Impressive, right? Okay, so we've reminded ourselves how to explain M and B. That was from chapters 1, 2, and 3. And then what we did in these last few videos, how to explain B and A for an exponential model. There we go. Okay, so what's next? Oh, a modeling problem. Okay, so we have the federal debt in billions of dollars is shown for various years in the table and scattergram below. Let T represent the number of years since 1960. Okay, so here are all the years. Here's the federal debt in those years, and you can see these dots, right? That is a scattergram of this data, these data, I should say. Okay, so we need to first answer whether it would be better to perform a linear or an exponential regression for this. Is it better to use a linear model or an exponential model? And hopefully, rather obviously, you can see exponential is better. This is going to become very important to you during your projects. So this is exponential. I don't know why I did that. Exponential is better because the data points form a curve, a rather classic exponential curve, to be honest. All right, so now we're going to have to find that model, and you know what's coming, hopefully, because you've been in this class long enough. You're going to have to find it using regression, right? That's the best way because it will use all the data points. So it's since 1960. They give us a starter year right here, since 1960. So we're going to have to figure these out. So this is 0. This is 10. Let me bold these. 0, 10, 20, 30, 40, 46, 51. All right, so now we're going to put this column of t values and this column of y values in our calculators. So let me go to, I can clear all that out. Stat, edit, go up and press clear, go over and up and press clear. We want, was it 0, 10, 20, 30, 40, 46, 51. And then over here we want 291, 381, 909. There we go. I think I got all those right. Okay, so then we are going to go to stat. Going to go to calculate. We see number 4 in there. That's what we used when we wanted to do linear regression, but that is not what we're interested in. There's a whole bunch of regressions in here. We're looking for one in particular. Oh, there he is. He's number 0. Exponential regression. He's our friend. All right, we want to find the exponential model for all of this. Okay, so I'm going to grab 0. It's asking me where's my x data, which is an L1. My y data is an L2. Great. Don't worry about frequency list. We don't work with that in this course. If you have any desire to store your equation, you can hit variables, y variables, 1, 1. And again, you do not have to. If you want to store your equation, knock yourself out, but it is not required. And then go down to calculate and press enter. And it runs it. And there it is, 224.057 or so, and 1.084 is your B. Don't worry about the R squared and the R. If they don't show up for you, I have a special calculator feature turned on. So all you care about is the A and B at this point in this course. We'll talk about R squared actually later on. Okay, so we've got our model. And it was, they give us a variable T. They don't tell us what the other part is, so I guess we don't care. So we could say debt is equal to, let me make it D of T, debt of time is 224.057 times 1.084 to the T. And there we go. All right, now let me double check those numbers real quick. 224.057, yep, and 1.084, perfect. All right, what was the coefficient and what does it mean? Well, it was 224.057, right? So A equals 224.057. What does it mean about the U.S. federal debt? In 1960, the federal debt, the U.S. federal debt, was about $224.057 billion. 0.057. Sorry about that. Great. All right. That wasn't too bad. Now the base. That's always the hard part. Okay, so the base B was equal to 1.084, which we all know is 108.4%. So now you take 108.4% and always subtract 100. Because remember, we're only interested in the increase. The 100% just gets us the amount we had to begin with, which is 8.4%. Okay, so here's my base right here. So I'm going to underline that. There we go. Okay, so what does this mean? This means that every year, the federal debt grows by about 8.4%. Done with that. All right, predict the federal debt in 2017. Is that interpolation or extrapolation? Okay, so remember that 2017, we want to take away our starter year, 1960. And that would be, let me do it this way, would be 57, right? Yeah, 57. Okay, so that's our t value, right? Okay, so I'm going to take my model and I plug 57 into it. D of 57. Okay. So I'm going to take 224.057 times 1.084 to the 57. Enter. And you get 22234.512. And just for fun, I want to show you, if you store the equation, which I did, and then you go down to 57. Actually, I'm going to show you the fast way. If you go second window, you can tell you want the table to start at 57. Then you go back to the table, and it'll start at 57. It's beautiful. There you go. So you get 22273.2 right there. So you can see if you have the calculator stored, it's keeping all those decimal places. It kept all the decimal places for the 224 number and for the 1.084 number, so it makes it so that it's slightly different, right? So you get 22273.217. So me personally, when I graded, I give both of those correct answers as long as the person shows their work, but you'll have to abide by whatever MyMathLab and or your other instructor wants. So we got, when we put it in the calculator the first time, we got 22234.5. So let's write that. 22234.51. All right, so what would that debt be? Oh, we better give it units. This is dollars because it's the US. And then we would want to say that it's billion. So think about what that means for a second. We're talking about 10,000 or 2,200, blah, blah, blah. 22,000, there we go, $22,000 billion. This is a huge amount, right? This is past trillion, right? So, or is it trillions? 22 trillion. This is large, large, large sums of money. So we could actually say it that way. So it's 22 point. If you want to move it to trillions, so here's how it goes. This is the billions place, 10 billions place, right? Hundreds billions place. And then you go to the trillions place, right? And so that's trillion. So it's $22.23451 trillion. Or, so you could write it either way. Both of these are correct. And it's a lot of money. And there we go. Done. Oh, and just one last thing. That is extrapolation, right? Because you're talking about the future. There we go. I changed how that looked. All right, we're done with that. I'll see you back here for the last problem.